in the screen? Okay. Sorry. Yes. Okay. Sorry. Okay, so I'm very happy to be here. It's amazing, and so it's fantastic to be in Seoul, and I would like really to thank the program committee to have suggested my name. So today I would like to take some time to discuss some latest results in my experiment in Innsbruck dealing with ultra-cold erbium atom. And actually I will discuss about two different experiment. The first one is in a lattice confined system, which have been done in collaboration with the group of Peter Zoller, so Peter, Misha Baranov, and Sikai. And the second experiment is really very fresh on CondMat, is on today CondMat actually, and is about asking ourselves what happens when we have a dipolar BC with attractive interaction. And this is in collaboration with Luis Santos and Falco Weckler from the University of Hanover. So let's start with the first topic. So we already heard by Randy how fascinating is the physics of lattice confined system and ultra-cold atom, and how is the ability to study different properties and to see very special correlated ordered phase. And from the first observation of the superfluid to Mott insulator transition, the field of lattice confined system has diversified very much. I mean, there are a lot of beautiful experiments about making the geometry of the lattice itself very exotic and even including some frustration. And some other experiment, I mean, as also we heard today, is about studying multi-spin, let's say lattice spin model, or for example, even to add some kind of disorder in the lattice and study physics of Anderson localization. So these are just a snapshot and just few examples, and of course there are many more and great achievements to be listed, but what maybe the point I would like to make is that in general, in this experiment, the interaction between the atom is of contact type. So it's an interaction, is the very well-known interaction for many of us in our community, which depends from a single parameter, which is the S-wave scattering length A, and this parameter can be tuned by the use of a Feshbach resonance, so it can be large and positive or larger negative, but is an isotropic interaction of short-range nature. So the question we wanted to pose in our experiment using a highly magnetic atom is how the Bose-Hubbard Hamiltonian, so a lattice confined system, is modified when we add a long-range interaction to the system. And the long-range interaction we have in mind is the dipole-dipole interaction, which fell down like 1 over r to the cube. It's dependent on the strength of the dipole moment, which in the case of atoms, it's the magnetic atom moment, but we will hear, I think on Friday, more talk about that with the ultra-cold molecule, in which the dipole moment is an electric one. And so the dipole-dipole interaction is long range and is not isotropic. It is an anisotropic interaction, and the anisotropy is governed by the presence of this angle theta, which is between the orientation of the dipole with respect to interatomic axis. So you can already imagine that if you have a long-range interaction, then the Bose-Hubbard model, it's also enriched by off-site interaction. Let's say atoms do not only interact when they are on a same lattice site, but there is this long-range interaction between and crosstalk between neighboring sites. And of course, if your parameters are, let's say, good enough, you can even study nearest neighbor interaction and so on and so forth. So these physics have been extensively theoretically studied, and here I report a couple of very, very nice reviews which I suggest you to look at. One, for example, thinks is that the phase diagram that we are used to with the isotropic contact interaction, which is the phase diagram from the superfluid to the Mott insulator and show all this sequence of lobes. In the case of, for example, 2D hardcore bosons, so basically we are thinking about a lattice-confined system in 2D in which only nearest neighbor dipole interaction play a role, have been studied in several theoretical papers. This is the picture from a paper from Capogrosso Sansone, and you see how the phase diagram change. And one thing which is very interesting is that density modulations start to appear in a kind of exotic phase, as they are called, like, for example, the checkerboard phase here. So we wanted to address the question of a Bose-Hubbard model with long-range interaction using erbium, which have a magnetic moment of 7 μb. And because of the special dependence of this long-range interaction, we wanted to use a short wavelength lattice so that the atom off-site can interact more prominently. So we have here lattice spacing of 266 nanometer. And in this type of system, the Hamiltonian that one should write is an extended version of the one that Randy has introduced to us before, because you have the single particle hopping as usual, and then you have an on-site interaction term, but then you have this additional direct nearest neighbor interaction, which is dependent on the occupation on site I and site J, and this coefficient here, this Vij, depend on the dipole moment. Another thing that one should notice here is the presence of the two term in the contact interaction. So this is the interaction when two atoms are in the same lattice side, and you have the usual on-site contact, which you can tune with the use of a Feshbach resonance, but in addition, you have a dipolar on-site interaction. And this dipolar on-site interaction depends on the angle of your dipole, so now you can tune it just by changing the orientation of the magnetic field and depend on the geometry. It's depend on the geometry, it's explained in this sketch here, because for a given orientation of the magnetic field, let's say like this, two atoms in a single lattice side can organize in such a way in which there is attraction, so head-to-tail attraction, or they can organize in such a way so there is a repulsive side-by-side configuration. How do you force the atom to prefer this configuration with respect to the other? In the experiment, it's pretty simple. You change the power of your optical lattice, you change the aspect ratio of the single lattice beam to favor this configuration over this one. So the first thing we did in our experiment is actually to focus on this on-site dipole-dipole interaction to prove that it's playing a role, to quantify the role, and also to study the geometry dependence. And if the on-site interaction is different, of course, the point of transition from a superfluid to a Mott insulator also changes. So we then drive by increasing the lattice power, the usual superfluid to Mott insulator transition, and probe the size of the central peak, which is very small in the superfluid and pretty large in the Mott insulator state. And we did this then for one orientation of our dipole, so like this one is attractive orientation, and then we simply rotated the angle of the magnetic field without changing his mean value. And then what you see is that the phase transition actually gets shifted now only by changing the orientation of a magnetic field. This already tells you that the Mott insulator phase is changed, and that in the phase diagram, the size of this lobe should also be changed. But what we did also to quantify this effect, so the effect of the on-site dipolar interaction, is to focus in the Mott insulator state and measure the energy gap of the Mott insulator. And this is, we used a technique which is very well known and very powerful, and this is modulation spectroscopy. The main idea is that one modulates the power of the optical lattice to drive resonant tunneling of one atom to the next site. And then, of course, here there is a gain of energy because now there is this additional on-site interaction. This is very well known for contact interacting system, but if now you have a dipolar object inside, depending of if they're, how they are oriented, this can mean that the gap of the Mott insulator state is larger or smaller. So this means that when we find for resonance, the resonance position corresponding to this configuration or this one should be different. And this is actually what we observed, and now if we compare the blue and the orange geometry, so you see clearly that the resonance position which kind of measured or give the energy of the gap have a shift in frequency, which means a shift of energy. We quantify this effect by also changing the geometry to make the dipole-dipole interaction more prominently attractive or more prominently repulsive. And what we see, this is the case, the dotted line is the case for purely contact interacting gas, and what we see is that by changing the orientation, we can still increase the gap or decreasing, also depending on the aspect ratio. And this is not a minor effect for our system, because the energy difference between these two configurations is something that can go in the order of alpha kilohertz. So it's something important and very sizable. So we have now the dipole-dipole interaction that can protect the Mott phases or can even attack the Mott phases. And the other very important term in the Bose-Hubbard Hamiltonian that really would drive these density modulated phases, it's the nearest neighbor interaction. And so we wanted to measure and to prove the existence of this term in the experiment. So of course, you can immediately imagine that if you have two atoms on the same lattice side, they are very close together. And since the dipolar interaction is distance dependent, it's stronger than in the case in which two atoms are in two consecutive sides. So it was sort of an experimental challenge to really measure and quantify the nearest neighbor interaction. But what we did is the following. We focus on a 2D plane in which all the dipole, we had one dipole per lattice side. Now, I depict here in green, no, not in green, in red, what I call a bond of repulsion. So these atoms here is repulsively interacting with this one, but is attractively interacting with this one. Now, if you have a purely contact interacting atom, short-range interaction in the system, of course, there is no crosstalk between atoms in different lattice sites. And so that means that if I want to resonantly drive the tunneling in this direction, or I resonantly drive the tunneling in this direction, there is no difference in energy. It's completely equivalent. I should get the measurement of the Mott gap exactly at the same value. But if, in contrary, if you have nearest neighbor interaction, since it can be repulsive or attractive, if now I drive, so I modulate the optic depths in this direction and I drive tunneling in this direction, what I'm doing, I'm destroying actually a bond of attraction. While if I do in the other direction, in the y direction, I break a bound of repulsion. So there is a mismatch between modeling along x or modeling along y. And these two configurations correspond to two different energy. And so by measuring the energy difference between these two configurations, this is a direct measurement of the nearest neighbor interaction. And since you measure energy difference, you get rid of a lot of systematic that you might have in the experiment. And when we did this, we indeed measured a nearest neighbor interaction which well agree with the one that one would expect by our theory. So one key point, in all the physics I was discussing with you today is the relative weight between the long-range dipolar interaction and the short-range contact interaction. So the relative weight between these two can be actually parameterized by the parameter epsilon here, which is the ratio of the dipolar length divided by the scattering length. Now, the dipolar length, which quantify the dipolar interaction, is given in terms of quantity that we know very well, the mass and the magnetic moment. So in the case of erbium, this is about 66 A naught. Whereas the scattering length is highly unknown. And as you might know, in a complex multi-electron atom like erbium, the scattering physics is very complex. However, we did some preliminary cross-dimensional thermalization experiment, and in this experiment, we measured the scattering length far from resonance. So, and all of the measurements I show you so far, those are focused on the isotope 168, which have a scattering length high in the sense that the parameter epsilon DDD is smaller than 1. So contact is kind of dominating over dipolar interaction, unless we don't use flashback tuning. But look here, we have another very interesting isotope, which is the 166. This has a lower background scattering length. And without any flashback tuning, this isotope allows us already to reach a value of epsilon DD about 1. And so we produce a Bose-Einstein condensate for our last paper of 166, which also well behaved like 168. And we wanted to use now this isotope to study the scattering physics. Another very important and very nice surprise we got from this isotope is that it has a flashback resonance almost at zero magnetic field. We very carefully map the conversion from scattering length to magnetic field using our 3D lattice, as I explained it before. So now we know very precisely the scattering length, and as you can see, around zero magnetic field, we can tune smoothly and nicely the scattering length. So this allows us in a very controlled way to change from epsilon DD smaller than 1, so contact interaction is larger than the DDI, to the interesting region where epsilon DDD is larger than 1. And also, focusing in this region, very important for us was to quantify the role of three-body losses that very often are an issue nearby a flashback resonance. And so here we also provided the recombination rate coefficient nearby a flashback resonance. And if you look at this number, actually, they are pretty good considering that we are close to a resonance. So rubidium out of resonance more or less is in this value of L3 for the expert. And now the question is, what is the fate of a dipolar BC with attractive interaction? So if we have a normal Bose-Einstein condensate with contact interaction and we make the contact interaction attractive, we know the answer. We can change the flashback resonance and make the attraction in the interaction. And then we know that in the case of the scattering length is smaller than 1, so attraction, the system globally collapses. This we know, and these have been also very nicely confirmed by early experiment in the group of Eric Cornell, in which he observed an isotropic collapse, then called Bose-Nava type of collapse. Now, what happens if we make attractive interaction in a dipolar BC? So with our intuition, as soon as you have attractive interaction, no matter how you get it, you should have a collapse anyhow. Okay, so here it's the mean field interaction for our system, so the contact and the dipolar, all of them are tunable, and in fact, back in 2008, in the chromium experiment, it has been observed that if your interaction is attractive, the system collapses. But you can already see something very exotic, and it's the pattern of the way the atoms are collapsing. They explode following a D-wave type collapse, and these are in the group of the observation in the group of Tillman-Fau. Okay, now so far so good, everything fit with our intuition. But then it comes really a big surprise when moving from the era of chromium to the era of lanthanide. So with lanthanide, as I showed you, it can be possible to produce epsilon dd equals to 1 already without any tuning of the scattering lens. And so in this condition, just a few months ago or half a year ago, the dysprosium group by Tillman-Fau in Stuttgart showed something very surprising and very nice. So what they observed is that for attractive interaction, the system does not collapse. This was really a big surprise and also completely not expected. And then, okay, it's not collapsing, but what this system is doing, this is the geometry used by the dysprosium experiment in Stuttgart, and what they observed that instead of collapsing, they kind of form an array of small systems which are called droplets. Let's say an array of a crystal kind of type of droplet when you bring the system to attractive interaction. And then, of course, when we saw this, I mean, it was very fascinating, and many people asked themselves, why, what's the origin of the effect? And from our point of view in erbium, we asked ourselves, will this type of physics also be observed in erbium? And we had a slightly different geometry, and what we can see, yes, we see a train of droplet, I mean, this is also depending on the geometry, also in erbium. But now, if we make a step back and we look at the Hamiltonian of the system, see, this is the Hamiltonian kinetic energy, trapping potential, and then you have the mean field energy, contact and dipolar interaction. Now, with this Hamiltonian, it's not possible to explain the formation of this type of droplet. This was very clear and very clearly stated from the first observation in dysprosium. You need something else, not only to see the droplet formation, but also to protect the system from collapsing, because this system was not collapsing. The lifetime was pretty large. And so in general, whatever you add, that additional nonlinear term in your energy, which has a density dependence larger than the one that you have for contact interaction, this type of physics can appear. And so that's the reason why it was first, let's say, suggested that maybe this additional term is due to genuine three-body forces. But then, following a paper, I think, from Dima Petrov and additional observation in dysprosium, there was very suggestive evidence that actually this additional term is the quantum fluctuation. So everything we have discussed in terms of collapsing and non-collapsing was in the mean field. But actually, you have correction to the mean field, and the first correction is known as the Lee-Wan-Yang. And so maybe this, in the form of the chemical potential, is more familiar to you. And so, and several triggered by this second experiment in dysprosium, many other theoretical groups also started to study this and also calculated the phase diagram. I mean, here it's two relevant papers for the phase diagram of now this dipolar BEC with attractive mean field interaction. You see, you have the usual mean field region, and then when you change the scattering lens, you will enter in this multi-stability region, where is the region where you see many droplets, as I show you. But there is also another interesting region, which is a region, it's not a phase transition, but is expected to be a sort of crossover to a region in which the dilute system would now kind of modify themselves in a single high-density state which remained a single droplet. And this is the region where we wanted to explore in the erbium experiment. And I also want to point out that there are very related experiments going on in dysprosium. So we then decided to produce a system in which we want to be extreme. So we make a very elongated system. Lambda is about 0.08, and we have the dipole aligned in this direction to get maximum attraction in the dipolar interaction. And then what we see is that if we probe the density profile for epsilon dd smaller than 1, this is a normal BC. So the dashed line here is the usual Thomas Fermi distribution. And now, when we increase epsilon dd, look at what happens to the density distribution. We have this formation, this smooth transition to a very high density state, and the difference in density is really remarkable. And then if we go even to larger epsilon dd, this shape of the high density state is still preserved, but you see that the peak density is smaller because you also have 3 body losses, as you would expect. Okay, so and then we could reconstruct the in situ atomic density, and we see a smooth crossover from what I call a dilute BC, so kind of an ordinary BC, to this high density droplet-like state. This is a smooth crossover, although the density, the reconstructed density, really increased by about 1 order of magnitude in this droplet regime. And this defines epsilon dd equals to 1. Besides the static properties, we also wanted to look at the expansion dynamics, and for the dysprosium experiment, I would like to say that Igor Ferrier-Barbout has a poster at the ICAP. I think very related result to this. So this is the expansion of a normal BC. So you have the BC in a trap, you switch off the trap, of course it falls down by gravity, but also it's free expanding. Okay, so and this is the normal BC with some correction because still the dipolar interaction play an important role. And now when we go to the droplet regime, as you can see, is really not expanding very much. So there is a drastic reduction of the expansion velocity. And this is, is what we have studied carefully. And so from this is the sigma as a function of the expansion time. And so the slope here give you the expansion velocity. And what you can see is that the expansion velocity as you enter in the droplet regime really decrease substantially. And the way it decreases can only be described from a mean field from a behind mean field theory, which account for quantum fluctuation, so correlation of high momentum state, while the normal mean field theory would not be able to reproduce this reduction of the expansion. The thermal components stay almost constant, and when we decrease even further, I already told you 3 body loss set in, and there's the effect of unbound your droplet, and so the expansion velocity increase again. This theory also accounts for 3 body losses. And the final, in the last minus minute, which I have, the last observation was about collective excitation. We know in our community that collective excitation really are kind of the ultimate test to check for interaction in our system. It was pointed out back in 2008 that the Li-Wan-Yang would affect any collective excitation which have a compressional character, so that depend from delta N, the change of the density. And in general, collective excitation have been observed already in contact interacting gas, both Fermi and Bose gas. And we want to focus to the collective excitation, which is called axial. So it's the axial, so the change, the oscillation of the length of our condensate. And now for this, we use this vertical imaging. So we are probing how the length in this direction, the axial one, is oscillating. We do this for many different scattering lengths. We have under control all our statistics. And then again, here we change the interaction in an adiabatic way, and we again see that the frequency of the excitation is increasing, and this increase can only explain it quantitatively by a theory, which is, by the way, no parameter free in the theory, which very well describe the system. And similar things we also observe when we quench the experiment. You see the system should collapse here if it's within the mean field treatment, but Li Wan Yang is stabilizing. And so with this, I mean, I think that what I would like to show you is this crossover from a dilute BC to a high-density state of the droplet-like type. And I want to present the group in Innsbruck which have done this experiment. I mean, especially the people in yellow, dark yellow here were really leading person for the experiment I show you. And with this, I would like to thank you. Okay.
There is time for a few questions. Yes. If you can find a microphone.
Thank you. I have two short questions. So firstly, usually the Li-Hua-Yang correction is quite small compared to mean field energy, right? So why so little correction can overcome the collapse?
Yes.
So the second question is
okay,
why?
Let's start with the first.
Okay.
So the first, I mean, is a good point I should have stressed. You have now three interactions in your Hamiltonian. The mean field contact, the mean field dipole, and the Li Wan Yang. Now, make the mean field contact and the mean field dipole such that they almost compensate. The system remain with the Li Wan Yang. And this is the driving energy interaction in the system. Second question?
Why there's no droplet in chromium BC? Why chromium BC
Yes,
collapse?
I mean, this is also a very good question. The parameter space is very large. So lambda, the aspect ratio of the trap, the dipolar interaction, but also the three-body rate coefficient. So both in chromium and in erbium 168, I could not show it, this epsilon parameter without Feshbach tuning is smaller than 1. That means that to enter in a regime of very big dipolar interaction, we have to heavily tune the system with the Feshbach resonance. And closer you go to a Feshbach resonance, more important are the three-body rate coefficient, so three-body losses. So this is the reason why I believe that in chromium or in erbium 168, it was not possible to see the droplet, but rather to see the collapse. So you see it's a multi-parameter space, and we, together also with the group of Tillman-Fau, so we try to address the different parameters.
Thank you.
Another question, anybody? Maybe I can ask, maybe it's a naive question right here. So what's going on inside these droplets? What's the structure of the atoms? Is there any hope of maybe doing something that our previous speaker spoke about, doing some kind of Bragg detection or even imaging of the atoms themselves?
So my understanding is that so from the first observation of droplet to today, just kind of a few months have been passed, and both groups are really now working to characterize the property. Like, for example, we observed now this self-bound character. Also, I mean, in other paper that will soon appear from this program, they also studied. So we are characterizing the system, but I think that there is a lot to still, especially in the collective excitation, to explore more. I mean, you just have to give us a little bit more time.
Okay, more to come.
Yes.
Okay, if there are no more questions, I guess we'll close the session and thank both speakers.
Thank you.
Our organizer, Cho, has something to say.
Yeah, we are like 20 minutes behind schedule. So the coffee break is until 4:45. So the next session will begin at 4:45. And there was one mistake in our abstract book. Professor Fau's poster abstract was put in for his invited talk. So his invited talk is on Wednesday, and we'll prepare a corrected version and put them on a registration desk. So this is the new title. I'm sorry about that.